Okay, we are recording.
Yeah, of course. Hello, everyone in the cities. Hello, everyone here. Looks like some of you haven't moved since I left you here 40 minutes ago at the end of EcoStats. So hello again. So thanks for having me here. I'm going to talk about one of my favorite topics, which is ice-covered winter on lakes. So the title of my talk is Impacts of Changing Winter Conditions on Lake Systems Will Increase with Latitude. So this is a paper that I'm sort of in the final stage of putting together, and it's the first time I've talked some of this stuff out loud, so hopefully it will turn into somewhat of a coherent story. We'll see. All right. Change. Let's see here, slideshow. This slideshow. For some reason, I have this.
Oh, I think we can just. Slideshow.
Okay, it sort of works.
Well, it's not changing up there.
I'll let you figure it out.
This is becoming a running joke, I think.
Okay.
Okay.
I think it's working. Okay, so mandatory climate change slide. Well, all know that the climate is changing. One of the big things that are happening is that the climate is warming. But this warming is not happening uniformly across seasons or across the globe. What we're actually seeing is that the warming is, first of all, strongest and most rapid with higher latitudes. So the Arctic and the subarctic are warming much faster than the equator and the temperate regions. And the other thing that we're seeing is that winter is actually warming faster than the rest of the year. So this is an example of a temperature record going from the 1960s to the mid-2000s, showing wintertime climate trends across latitude. We can see that, again, the Arctic and subarctic are warming faster than lower latitudes. And this pattern is actually forecasted to continue into the future. Here are some climate warming scenarios under several different temperature conditions, and you can see that winter, again, is forecasted to warm more than summer, and higher latitudes, again, are forecasted to warm more than lower latitudes. So winter is warming faster than the rest of the year, and high latitudes are warming faster than summer. Thanks, Jake. There we go. So one of the things that are happening with warming winters is decreased ice cover duration. This is a paper from Sharma et al. From a couple of years ago, showing ice on and ice off dates, ice on and ice off dates for a bunch of freshwater aquatic ecosystems that have really long records of temperature of ice cover. And what you can see is that ice on is getting later and later, and ice off is becoming earlier and earlier, with sort of the consequence that ice cover duration is decreasing. And of course, with continuing climate change, this pattern is forecasted to continue. So here are some projections for ice cover duration. So for ice on being later in the future and ice off becoming earlier. So what is happening? Again, winter is warming, ice cover duration is shorter. There are changes to precipitation in the winter, snow retention over the ice, rain and snow events, and a whole bunch of other stuff that's happening on lakes in the winter. One of the challenges that we're facing is that winter has historically been sort of neglected by limnologists. It's cold, it's gross. I'm here, I'm stuck, but happily teaching my classes, which means that I can be outside collecting data. And this sort of neglected winter has resulted in the general idea that winter is boring, nothing interesting or important is happening in the winter, and consequently there is no need to study it. This sort of loss of winter and decreasing ice cover duration has spurred a lot of limnologists to take a second look at winter. So there is a rapid growth of interest in winter, and people are trying to close this big knowledge gap that we have traditionally had about winter and what happens when lakes are covered by ice. So a lot of this work on winter, let's say, it's not that no one has ever worked on winter. People have been working on winter for decades, but let's say a lot of this interest started happening in the last 10 years or so. But because this work, at least in the scale it's going on now, is relatively new, and because people are geographically based, a lot of this work is ecosystem specific. Right? I go to my 3 lakes that are nearby, I study those 3 lakes, and I gain some understanding of how these 3 lakes work in the winter. People, let's say in Finland, go to their lakes, study their lakes. We're sort of doing our localized work in our different regions. I think we're getting to a point in winter limnology where we're sort of starting to look for big conceptual frameworks, trying to put these localized ideas together to gain a more general understanding of what winter is like during ice cover and what the loss of ice cover means. So I've been doing winter work for more than 10 years, and I've been really fortunate to work in all kinds of different ice covered ecosystems. So I really got excited about winter work when I was doing field work in Lake Baikal. I spent 3 weeks in winter on Lake Baikal, a really interesting and unique lake. And doing some of the work there got me really, really excited and really interested in what's going on under the ice. We saw some really cool things with phytoplankton, zooplankton, and I was sort of hooked on winter. So after doing the work in Lake Baikal, I came here to UMD, and I got a chance to work on a whole bunch of lakes around Minnesota. So here's some work on Lake LaSalle in western Minnesota. I did a bunch of work on Lake Superior in the winter in different locations in Lake Superior, both during ice-covered winter and also ice-free winter, small boat. I got to do some work in boreal lakes in central Quebec, very, very different lake types and very different conditions. And even a bit of work in the high Arctic. This is a lake outside of Tromsø, Norway. So over my 10 years, again, I was fortunate to see different kinds of lakes in the winter with very different winter conditions and also different limnological conditions in these lakes. And during this work, I started to think about, well, how to put all these experiences or ideas together into something coherent. So last year or the year before that, starting to forget now, I took a sabbatical and I went to Norway, where actually I went to Quebec as well, but I spent a bunch of time in Norway, where I collaborated with my longtime colleague, Dr. Amanda Post, who's at the Norwegian Institute for Nature Research, and also collaborated with Mila Rautio, who's in Quebec, and Eva Lu, who's a Norwegian marine biologist. So what unifies all 4 of us is that we're really interested in winter, but we work on winter in different regions. And as we sort of got together and started talking, we started putting our heads together to try to understand what winter really means across these big gradients of water quality or latitudes where different people are working, and where winter can look very different. So this presentation is based on those conversations and on a paper that we're, like I mentioned, almost finished writing and hope to submit in a little while. That's, we hope, is our contribution to making sense of winter. So let's go way back and think about solar radiation as it hits the Earth. Right, so we're sitting somewhere around here. What we're plotting here on this is sort of a contour plot of solar energy reaching the Earth across different latitudes and across the annual cycle. You see this DOI in one of my graphs. This is day of the year, right? January 1st to December 31st. And depending on where you are in the globe, the amount of insolation that you receive varies, and the seasonality of solar insolation changes as well. So from the equator to the poles, there's approximately 2.5-fold decrease in total incoming solar radiation. But there's also a difference in seasonality, right? So near the equator, the solar flux is nearly constant, And as you move further and further away from the equator, you get more and more variability, where the point where you're above the Arctic circles, you end up with periods in the winter where it's completely dark for part of the year, and periods in the summer where you have the midnight sun, right, where it's always light. And of course, the further north or south you go, the more extreme the seasonality is. So far, so good. It makes sense. You remember that from grade school? Good. So part of one of the consequences of this variation in insolation, moderated by a whole bunch of Earth science, is of course the climatic variability that we see from the equator to the poles. It's closer to the poles, and one of the consequences of this is a more severe winter as you go further up north. Moderated, of course, by continentality, ocean currents, but the general pattern is winters are colder, longer, and more severe the further north or south. An obvious consequence of that is that ice cover duration on lakes generally increases with latitude. Of course, moderated by regional climate and elevation, but looking at the big picture, the further north you are, the longer the ice cover duration. And this is some data that we replotted from a recently satellite-based inventory of ice cover duration on the globe. Again, you can see the farther north you are, the closer you are to a very big chunk of the year being ice covered. So you also probably know from Limnology 101 that lakes are not evenly distributed across the Earth's surface. And so here is a figure from Denfeld showing the abundance of lakes across different latitudes in the Northern Hemisphere. Very few lakes in this region. And as you get sort of in the temperate, boreal, and subarctic and Arctic regions, you see this increase in lake numbers and, of course, lake area as well. Most lakes are further up north. If you sort of superimpose the amount of lakes that freeze on this figure, right, shown here in blue, you very quickly realize that most of the world's lakes actually freeze for at least part of the year. If we look at that WANG data from before, this is their lake distribution. They only include lakes that freeze, so that's a little bit different. But here's the distribution of lakes that freeze. There are, of course, lakes that freeze here at very high elevations. There are some lakes at mid-latitudes that freeze, but sort of reflects what we know about distribution of lakes and direction. And what I superimposed here is their data on lake ice cover duration. What you can see is that once you get to slightly above 50, 4 degrees latitude, lakes are ice covered for more than half of the year. Right? Again, notice that a lot of lakes are above this line. So in fact, not only most lakes freeze, but most lakes are frozen for more than half of the year. If you look at the median ice cover duration of lakes that do freeze, lakes that do freeze, it's 218 days. So the median ice cover duration is approximately 2/3 of the year. Pretty impressive, right? So a lot of lakes spend a lot of their time covered by ice. So understanding what happens under the ice, of course, is important. Okay, let's go back to this figure. So as we started thinking about these different lakes that we work in and what winter looks like there, we sort of try to superimpose what we know about the polar insolation pattern with what we know about ice cover duration. So it's the same plot showing watts per square meter per day across the year, across latitudes. And what we're, which way is down? What we're superimposing here is average ice cover duration with latitude. These lines show one standard deviation. This is just the mean. Couple things to note here. One, of course, ice cover duration becomes, like I said, an increasingly large portion of the year as we move further north on average. Right? The other thing that you may note is that as you move poleward, ice cover increasingly overlaps with the most light portion of the year. The point where when you're above approximately 65 degrees latitude, during midnight sun, the time where you're getting most of your light, where light is most intense, your lakes are still covered by ice. So part of what the point that we're trying to make here is that we believe this interaction between ice cover duration and the seasonality of solar flux has not been well recognized, especially this fact that the farther north you are, the more of your well-lit peak light period you're actually experiencing ice cover on lakes. Okay. And we think this interaction between seasonality and ice cover duration has some really interesting and we think underappreciated consequences for lakes physics and for lake ecology that I'll try to explain. So same idea. So if we sort of disregard the effects of ice and snow on under ice light and just look at how light energy reaches the landscape, so that very clearly or not, but I try to explain. We'll see that first of all, like I said, as you move from the equator forward, total light energy reaching the landscape during the year decreases, right? So far, so good. What we did here is we looked at the portion of light energy reaching the landscape while the lakes are ice-free versus while the lakes are ice-covered. And notice that these two lines are opposite of each other. The further north we go, the more of the total light energy proportionally reaches the landscape when the ice is still on the lakes. Right, to the point that where you're approximately above 65 degrees latitude, most of the energy that the landscape gets is received when there is still ice on the lake. So this is, for example, a picture I took in Norway when I was there. This is a lake about 200 meters above sea level, so by no means a mountain lake. And this is a week after the summer solstice, right? So it's light day round, night round, and the lake is still covered by ice. Okay, are we sort of on the same page about this idea of the interaction ice cover duration and seasonal variability of light flux? Okay, so this is sort of what we're building this thing from. Now, of course, the light that reaches the landscape is not necessarily the light that reaches the lake and is available for photosynthesis or heating or mixing the water. This is strongly moderated by ice and snow cover. And depending on where you are or when you are, your ice can look like this. This is a picture from Lake Superior, right? Perfectly clear black ice, probably about 2 feet of this very, very clear black ice that transmits probably 85% of the photosynthetically active radiation that reaches its surface. This is a picture I took when we were working in Quebec. And here you have 2 feet of snow, you have 2 feet of slush, and then you have 2 feet of white ice. So under that ice, well, first of all, it's a pain in the ass to work there. And second of all, it is pitch black under that snow and ice cover, right? So ice, depending on how cloudy it is, has a KD of between 0.5 and 5. So it can either transmit a lot of light or attenuate a lot of light, but snow is very attenuating to light. It has a very high KD, and under even a foot of snow, you're losing 95, 99% of light. It depends on snow characteristics, but again, very strong filter for light. So what we wanted to do is to model light climates under snow and ice across a range of conditions and across a range of latitudes, taking into account different optical properties of snow and ice cover, and this again, latitudinal variation in ice duration and insolation. Okay, so far we're good. Okay, so what we did then is we created some scenarios for 10-degree latitudinal bands of ice cover duration, looking at median ice cover duration, long ice cover duration, adding a month. For example, situations you might see at high altitudes or at a very continental climate. And we also ran scenarios for a short ice cover duration. So either a very coastal climate or what we might see with ice cover loss in the future. And for the ice cover durations in these three scenarios, we varied KD, that is attenuation of the ice, of light by ice, from being very transparent to being quite attenuating. And we also modeled a whole bunch of semi-realistic snow cover scenarios. Some situations where we had no snow, some situations that are sort of more realistic where we had early winter, no snow, buildup of snow, and then melting of snow, and very little snow. And then, which is what we typically see around here, and everything in between, from like a totally unrealistic scenario when as soon as the ice is on, you get like a meter of snow and it just stays there until the ice comes up. Basically, we wanted to explore the range of under ice light climates. Okay, so these are the scenarios that we came up with, and we did it again from 45-degree latitude to 75-degree latitude and 10-degree latitude bands that I'm just not showing you here. So here is sort of what we got. Just as an example, so what we see here, the yellow line shows just potential insolation, not accounting for cloud cover because I simplify things. So again, so this is potentially how much light is available. Again, as I mentioned, right, there is a midnight polar where it's totally dark at higher latitudes, and there are periods where it's quite light, and here at lower latitudes, of course, it's less variable. And what these lines show is the different snow and ice cover scenarios, from a situation where we have very transparent ice with very little snow to situations where we have tons of snow and very opaque ice. So what this shows here is sort of the range of scenarios that you might expect the snow and ice cover to, how it might affect under ice flight climate. That's so far making sense? Okay, so we've just generated a whole bunch of different scenarios, and we want to see what the end result is. So what I'm going to show you is a few of the summary graphics from those simulations. What I'm going to show you here are the different latitudes, again in 10-degree latitude bands, our short ice cover scenario, our medium ice cover scenario, and our long ice cover. The different colors represent a different ice KD, from very clear ice to very dark ice, and within each KD category, there's a whole bunch of snow cover conditions. So there are several hundred scenarios of ice and snow clarity. And the different scenarios are connected by a line. So this is the same, no snow, very transparent ice at 45 degrees, 55. So what are we seeing here? So first of all, of course, as you might expect, this is a total annual light flux. As you might expect, the further north you go, the less light you get. That's quite obvious on an annual basis. But notice that there's quite a bit of variation as you start to vary the ice cover duration and the variability increases the longer the ice cover is. Because if you have a month extra of ice cover and the ice cover is clear versus you have a month extra of ice cover and it's totally opaque, right? This now has a much bigger effect on your total annual light dose. Okay. So total annual light dose decreases with with ice cover duration, but it also becomes more variable. That is, the ice and snow conditions play a more important role in affecting your total annual light budget. What this shows is the total flux during the ice cover period. And again, these are, of course, the more clear snow, less snow, more clear ice, less snow scenario, and here is tons of snow, very opaque ice. Again, what we're seeing here is that there is an decrease in total winter period light flux latitude. But what is interesting is that as your ice cover duration increases, more of the total light you're getting arrives during ice cover period, but the variability again is greater because if you have like 7 months of ice cover, but it's very clear with very little snow, like in the polar desert region, more of your light, of course, arrives in the summer, but you're still covered by ice well into this polar midnight sun period of time. What also changes is the ratio between the total amount of light that you're getting during the open water season and your ice cover duration. And again, as you move further north, and especially as your ice cover duration increases within these latitudinal bands, the proportion of your total light that arrives when you're covered by ice versus the proportion of total light that arrives when you're ice-free increases as well. And as you move further north, the characteristics of ice and snow have an increasingly large effect on how much of your solar radiation you're getting during ice cover versus during the open water season. Are we sort of on the same page here? Okay. Summarizing this, what I'm showing you here, slightly different graph, is how a month of less ice versus amount of more ice relative to the median affects the total light under the ice. So a percent change in light under ice, if you subtract amount of ice cover, remove 2 weeks from early and late ice cover season across, and what happens if you add amount of ice? Let's say you go higher in elevation or something. Again, notice that higher latitude systems are more sensitive to both longer ice cover duration and the loss of ice. And again, they respond in greater variability depending on what their snow and ice conditions are. So all this is to say that first, high latitude systems are more sensitive to snow and ice conditions because snow and ice cover there overlap more strongly with the peak period of light in the receiving light. And the loss of ice cover is going to have a bigger impact on the light dose of these high latitude systems. Because when you lose amount of ice cover here, you're losing amount of ice cover, let's say in April, March, right? When we're not at our peak solar insolation. If you're in Svalbard, you're losing amount of ice cover potentially in like June, July, which is where you're getting a huge proportion of your daily light flux. Okay. So in addition to this, ice, in addition to regulating light, also has a pretty large impact on temperature. So what I'm showing you here are temperature data, both real and modeled for, say, a typical lake in central Minnesota, along with insolation and let's say a average winter sort of situation scenario. So here's potential light, and here's actualized light under the ice and snow, and here is what the temperature data looks like. And this is the same data for a lake on Baffin Island in Canada. Matching data from Baffin Island in Canada, very high latitude. And again, much larger seasonality of light. And of course, quite a bit of a difference in temperature. So in central Minnesota, the ice comes off, the lake starts warming, and it gets to about 20 degrees latitude by midsummer, potentially peaking at 25 or maybe even 28 degrees Celsius until it cools down and freezes again later in the season. In contrast, on Baffin Island, or generally speaking, the high Arctic, heating starts much later, right? The ice off occurs somewhere around here. Heating happens later, and you never really get that warm. So this particular lake never really gets above 10 degrees or so. Some lakes, of course, in the high Arctic never get much above 5 or 6 degrees, right? So in addition to a difference in light climates, there's also quite a difference in temperature conditions with latitude. So we're making the case that this seasonality of light and temperature and the interaction with ice cover duration has important consequences for biology. I would make the maybe somewhat controversial statement that the 20th century obsession with eutrophication as the main light water quality issue has sort of fixated us on nutrients as one of the main driving forces of ecosystem dynamics. But there are more fundamental things that structure ecosystems, right? Light is really a very important limiting factor for primary production. And we often forget this, but temperature is a critical factor for secondary productivity of poikilotherms or ectotherms, right? So if you look at how secondary production is modeled, it almost always includes a very strong component of temperature. And if you look at the productivity literature in marine systems, you can completely disregard food availability and model production simply using temperature. Okay, so yes, I'm not saying that nutrients are not important, but I think over fixating on phosphorus made us maybe not forget, lose a bit of focus of light and temperature. So because light is a primary driver or a primary physical driver of prime production, and temperature is a primary physical driver of secondary production. Not that temperature is not important for prime production, but it's much more important for secondary production. We're going to make the case that this variability in light and temperature has important consequences for productivity and dynamics of primary and secondary production in freshwater ecosystems, both in the plankton and in the littoral benthos. So thinking about phytoplankton, thinking about periphyton, zooplankton, and thinking about littoral zoobenthos. So we made a very simple model of primary and secondary production and of primary producer and secondary and consumer biomass. We made the assumption that light is the primary driver of primary production with a secondary effective temperature, Q10s coefficient. So we assume the Q10 of 1.4, which means that primary production at the same light level for every 10-degree increases 1.4 folds, which is sort of like the literature empirically determined Q10 for primary production. So light drives primary production with a secondary effective temperature, and secondary production is driven almost entirely by temperature with a Q10 of 2.7. So for every 10 degrees, secondary production increases 2.7 fold, and there's also an effect of primary production as a secondary effect. So what we're showing here is primary production and secondary production of either phytoplankton or periphyton, and of either zooplankton or littoral zoobenthos at 45 degrees and 75 degrees, and also the accrued biomasses of primary producers and consumers, assuming some simple interactions between the two where they can graze. Again, this is a toy model. It's not supposed to really be super realistic, but what it's supposed to show is relative magnitude. And one thing that I want to point out is, and we ran this across all kinds of light regimes, this is sort of like a moderate ice and snow attenuation regime. The one thing I want to point out is because the light differences are not that huge during the ice off season between these two systems, is that the amount of primary production, while lower at higher latitudes, is not that much lower. But because temperature is a more important driver of secondary production, and the Q10 differs quite a bit between primary and secondary production, there is a much larger difference in secondary production between our warm lakes and these cold high latitude lakes. And because we have a term that involves regulation of primary producer biomass by consumers, the realized primary producer biomass at these high latitude lakes relative to low latitude lakes can be much higher, because these consumers have not been able to build a high biomass because of these cold temperatures at high latitudes, and they're less good at this top-down control. So the ratio between primary producers and consumers, we argue, should change predictably with latitude, where the ratio is closer at low latitudes than it is at high latitudes. What we're also saying is, depending on ice and snow conditions, potentially a larger chunk of primary production is possible under the ice at high latitudes. But that is going to strongly depend on ice and snow problems. The situation where you have very clear ice and snow, you can have a very large chunk of your annual primary production occurring under the ice, where temperatures are like around 0 and 4 degrees, and consumers are very inactive. You might be able to build a higher biomass of primary producers before the consumers are actually very active and are exerting a top-down control. So we run these scenarios for short, medium, and long durations. I don't want to spend too much time talking about squiggly lines, but basically we're making a couple of points. One is that the synchronicity between primary and secondary production, because the synchronicity between light and temperature are higher at lower latitudes, the synchronicity between primary and secondary production is going to be higher at lower latitudes. As you get higher at higher latitudes, primary production is going to happen earlier and be more decoupled from secondary production, which is sort of waiting for warmer temperatures to really kick in. There's going to be a greater decoupling between primary and secondary production, the phytoplankton and the littoral, and the plankton and the littoral zone. And with loss of ice, the synchronicity is actually going to increase more so at higher latitudes than at lower latitudes. The other thing we're saying is that the primary to secondary production and biomasses ratio, again, are going to be higher at high latitudes, and loss of winter is going to increase it more so at lower latitudes. So that's sort of the story, and that sort of comes back to this idea that our prediction that high latitude lakes are going to be impacted more by ice loss than low latitude lakes. And a lot of it comes down again to the idea that this is driven by the greater overlap between ice cover duration and the period of peak insolation as you go higher and higher with latitude. We of course glossed over a whole bunch of things. We totally neglected attenuation by clouds, which varies regionally. We pretended like nutrients are not a thing. Of course, there are latitudinal patterns in nutrient concentrations, although there are high nutrient ecosystems in the high Arctic as well. And we assume that we're working with medium lakes where euphotic depth and total depth are not very different, right? So if you're working in a very deep system where euphotic depth is much less than mixed depth or total depth, you're going to have to think very carefully about what actually happens during this part of the year where you're getting deep mix. So we simplified things, but we feel that because a lot of our assumptions are based on first principles, all of our ideas, if not hold, they propose interesting hypotheses that could be tested. And I would argue that right now there is simply no data sets or coherent data sets that can test a lot of our hypotheses about year-round function, because one, there is less data from the high Arctic, and two, very, very little global scale data about what happens in the winter and during transition seasons. So that's sort of the idea. And I'm open to the many questions that may have about their assumptions, ideas.
Thank you.
Yeah.
Rob?
Yeah, I have a question.
Yeah.
Have you played around at all with these higher latitude lakes getting above like 4 degrees C and then the changing stratification regimes, which like can drastically increase temperature, especially near Apollonia?
Yeah, I mean, what do you mean by played around? So, you know, here's an example again from Baffin Island, and this lake gets to about 10 degrees. This particular lake gets to 10 degrees max.
Yeah, but you said like a lot of these lakes are getting warmer than like 4 or 5, but
Some of them are
And
not.
like
Some of them are
one-
continually ice covered or have a 1 month ice-free period, and they don't get much warmer. Some of them do. So, for example, the lake where we were in Norway gets to about 15 degrees. So it depends on the regional climate. And of course, yes, shorter ice cover duration is going to mean more time for Apollonia warming and actually warmer temperatures. So it's,
Was actually super related. I was wondering if you were thinking about how changes in stratification as a result of longer ice free season might impact your primary production. And a lot of guys have really heavy phytoplankton really be impacted by whether or not they can stratify. But I know a lot of these things are shallow.
yeah, it's a good.
Jay, could you repeat the question for our remote audience?
Yeah, so there's a question about whether we considered stratification and how different communities are impacted. No, we haven't. So we've simplified things to the core, and I think we do need to consider stratification and mixing. But you know, if diatoms can't do well, then something else is going to use the nutrients and light that's available.
Yeah.
Question for you about testing this hypothesis. You mentioned very quickly, but in lieu of waiting to see what happens to them, how would you go about setting up an experiment now that could program this empirically?
I think so. There was a question about how to test some of these hypotheses that we're building here. I think the most straightforward way would be a sort of harmonized cross-latitude study that looks at the same data across the full year. We actually have some of this data for the open water season. And if you look at zooplankton abundances, for example, temperature predicts them very, very well. But we don't have this data for the winter. So I think you could start testing this by deploying sensors, the same suite of sensors across large latitude pattern bands and across these sort of like, continental to, let's say, more coastal gradient, where at the same latitude bands, you have different ice cover durations or different snow conditions to quantify this. And then track the development of phytoplankton and zooplankton through the year and see what shakes out.
Can you deploy the same sensors in the winter, like does ice cover affect what type of sensors you can have out?
Yeah, so the question was whether we can deploy the same sensors in the winter and summer. It's a bit more complicated, but yeah, you can deploy thermistors, you can deploy, we have some oxygen sensors in some lakes, you can put EOS or light bar sensors under the ice. So yes, it all becomes a bit more complicated because you don't want your surface buoy or subsurface buoy to freeze into the ice. But yes, you can, and people do. There's still a shortage of wintertime sensor data, but there's more and more coming online. Yeah, Quinn.
I have two simple questions.
Mhm.
What is like the definition of ice off?
Ice off is when the ice comes off the lake. So there is a period where there is maybe like some slushy ice or some chunks of ice floating, but I believe ice off is basically when the continuous ice cover breaks down and does not reform anymore.
Like 100%.
Yeah, it's the end of winter, or ice cover winter, or winter ice cover.
And then my other question was, I think it's like on your second or third slide, maybe, you had a graph of like the change of dates of ice on, ice off. Yeah, it looks like it's almost the Charlotte one. Yeah, yeah. It almost looks like it's like there might be changes latitudinally, but also coastal lakes.
Yeah, there's a fair bit of variability in what. So the question was about variation in ice cover duration, ice off and ice on. Yeah, there's a ton of variation. Again, that Wang paper that we used for one of the next slides, probably should use that as well. But yeah, depending on where you are, you're losing ice at different rates and projections are different. So in Minnesota, we lost about a month of ice cover in the past 100 years. Some areas are losing ice faster, and it relates to basically winter climate. Yeah, that's a great question. So there's a question about primary and secondary producers and community composition. Good question. As you move further north, or as things get colder, you lose cladocerans relative to copepods in the zooplankton, just because cladocerans like it higher than 15 degrees Celsius, roughly speaking. So there are differences in communities. You also get more cold adapted stenotherms at these lower, at these higher latitudes that can accumulate a lot of lipids that have long lifespans and sort of maybe complete their life cycle in 2 years. For the phytoplankton, I know a bit less, but for this paper, we're just totally ignoring all this obviously relevant and important variability to focus on light and temperature.
So with a lot of these lakes that are understudied, just because of geography and people that like to study under the ice, like, are there any topics that you want to get to quickly before climate change has impacted them too much that we're kind of beyond what the baseline was?
Me personally?
Yeah.
So the question was what topics I'm really excited about for myself. I think some of this stuff. So, we're proposing a very simplistic framework. I think filling in some of the details for that and also maybe thinking about the role of trophic status and how it interacts with some of this variability. So for example, if you think about an ultra-oligotrophic lake versus a dystrophic lake with a lot of dissolved organic carbon, some of these winter-summer differences are probably going to look very different in the dystrophic lake because there is this sort of large and maybe not very tasty, but large and continuously present pool of carbon that remains there. So how ice cover duration interacts with trophic status is a question that I'm really interested in. And because I'm an ecosystem to community ecologist, I'm most interested in like zooplankton, phytoplankton communities. Yeah, how they vary across large scales.
Well, I think that's a good question to end on. Thanks for coming to the TED Talk.
Yeah, my pleasure. Thank you, everyone.
Nicely done.
It's your bell.
All set down there? Diana, was that any better this time?